Sorry about that beginning. My iPad wouldn't actually start recording, so it needed to see outside, I think. Anyway, at the end of yesterday's class, we had drawn a picture like this, and I had given you the hand rule. So this is a solenoid, wire wrapped around an iron core or ferromagnetic core, hooked up to a power supply. Okay, so the core, piece of iron or whatever, isn't magnetic beforehand. But if we put it inside a wire that's coiled around it and run current through the wire, then we can make what's known as an electromagnet. Okay? And some of you talked about the fact that you did this at the Engineering Shadow Day. Okay? So this is an electromagnet. So as soon as I run current through, and I'm going to assume left-hand current, so coming from the negative side of the power supply, then current will go this way, will go this way, will go this way, will go this way. And so now our hand rule is, this time, you, down here where the wire is coiling, you curl your fingers in the direction of the current flow, and your thumb is going to point in the direction of the magnetic field. So, let me switch hands, because I should have done right hand. So, I'm going to curl my fingers up around like this, and my, yeah, it's not going to work. And my thumb, on my other hand, is going to point to this side, okay? And so, your thumb points in the direction of the magnetic field, which means the magnetic field is coming out of this side. And remember, field lines are closed loops, so if they're coming out of this side, it means they must be going in over here. And if they're coming out over here and going in over here, that means this must be like the South Pole, and this must be like the North Pole. And so it really, what we've created then is just like a little bar magnet, right? Which is why we call it electromagnet. So this is the north over here, this is the south. Now the cool thing is, it doesn't matter whether I do electron current or conventional current. I'm still going to get the field the same, going the same way. So this diagram, I'll just shrink this a little. This diagram, it's exactly the same as that one, okay? So I've drawn two of them that are exactly the same. If I go conventional current over here, okay, so I'm just going to blow this up so you can see it better. Maybe focus it. Maybe not. There we go. If I do conventional current on this one, then instead it's going down on this side then, and down on this side, which means down here, down here, down here, if you just follow the wire around, right? And then up here. So now for this one I have to use my right hand. So my fingers curl down in the front. My thumb still ends up over here, which means the field lines come out over here and go around in over here, which means it's still a south there and a north here. So it's still exactly the same as this one. So I don't actually need to tell you on these guys if it's electron current or conventional current. You can use either one as long as you use the appropriate hand with whichever current you choose. Then you will end up getting the correct side for the North Pole, the South Pole. Okay, so it's like it's creating a little bar magnet. And the field lines will look just like the field lines from the lab that you did. Now, before you begin to say, oh, so the negative side is always the south and the positive side is always the north, don't do that. It depends on the direction that the coils are being wrapped. So look at this one. Okay, so again, if I do electron current, it would come down here and then go up in the back, down in the front, down in the front, up in the back. And now if I use my left hand, impossible to do, just because of the way I'm holding that thing. My thumb ends up over here, which means my thumb ends up pointing out over here, which means the field lines will come around and go in here, which means this time this is the north and this is the south. So please don't be lulled into a false sense of, oh, the negative and the south are always on the same side. No, I'll find a way to screw that up for you. Okay? So that's just the end of what we were doing yesterday in class. It's called the right hand or the left hand curl rule. The other new piece that we would have done today was we would have talked about magnetic force. Okay? Magnetic force. And this magnetic force can be between two magnets. It can be between a current and a magnet, or it could be between a magnet and a moving charge. And that's because all of them will have, they all have to do with magnetic fields, right? Two magnets have magnetic fields around them. A current and a magnet, two currents, they all have magnetic fields around them. And so, like Justin said yesterday in class, magnetic force has to do with the interaction of the magnetic fields. So today I want to look at the force between a current carrying wire, and a magnetic field. Okay, so a current carrying wire and a magnetic field that is created by something else. Okay, so you could call it, if you want, an external magnetic field. We don't know if it's being set up by a magnet or by something else. Okay, so it's not the magnetic field from the current carrying wire. So let's suppose I have a magnetic field that's doing this. X's mean what? Hopefully you are saying they mean going into the page. And I left this little gap because I'm going to put my wire here. Okay, so here's my current carrying wire. It's carrying a current, let's say going this way. I'll put a little E here to make it electron current. Okay, so here's my electron current, here's my current carrying wire. The wire is going to experience a force in this magnetic field. So the first question would be, what do you think that force is dependent on? Okay, so it's definitely going to be there's going to be a force, and we're going to get both an equation and a hand rule. Well, one of the things it should be obvious that the force is going to be dependent on would be the strength of the field, right? The stronger the field, the stronger the force should be. So it's going to be dependent on B. Another thing that it should be dependent on should be the current, right? What size the current is. The bigger the current, it would make sense that there would be a stronger force. Another thing that might not be quite as obvious that the force is going to be dependent on is the length of the wire, L. Okay? And the final thing that the current is dependent on is the angle. The angle in between the direction of the field and the direction of the current, the theta. Now, as soon as you see theta, you should be thinking, uh-oh, dot product or cross product, right? Because if there's an angle involved, it means we're multiplying vectors. What we're getting out is force. If we're getting force out, that's a vector. And so you know from when we were doing vectors that the only way we get a vector out is if it's cross product. And so the equation is F is equal to B cross IL, because both B and I are vectors, right? The direction of the current is important, direction of the field. And so our equation becomes F equals BIL sine theta. Okay? And obviously there's going to need to be a direction, and so we're going to need a hand rule to get that direction. But first I want to just point out something that you haven't asked in the week since I told you magnetic field was measured in Teslas. None of you asked, what's a Tesla? A Tesla is really a Newton over an amp.